So the solubility of most solids increases with increasing temperature. Not all of them, but most of them. So like here's potassium nitrate, potassium dichromate, potassium chlorate. As we increase the temperature, the amount of solid that will dissolve in 100 grams of water goes up. Now sodium chloride has a rather flat curve here. It increases, but not very much. And then there's sodium sulfate. Sodium sulfate is weird because as you go to higher temperatures, it becomes less soluble. But that's not normal. That's the exception. So to make a supersaturated solution, what you do is you go to a higher temperature, maybe 55 degrees, and you get a saturated solution there. And then as it cools down, if it doesn't begin to crystallize, you cool it down to room temperature, you've exceeded the amount that can dissolve in that amount of water. And when it gets disturbed, it will precipitate out. Sodium acetate is a great one to do this with because it's like more clueless than the other ionic solids. You can fool it into becoming a supersaturated solution. Some of these compounds, you can go through the same procedure, but they'll just start crystallizing out right away. Recrystallization is a technique that takes advantage of this increase in solubility with temperature and uses it to purify solids. So when we collect a solid precipitate, sometimes it has impurities that co-precipitated with it, and we want to purify it. So you can take your solid that you're wanting to purify and dissolve it in water at a high temperature and form a saturated solution at a high temperature. And then you let it cool down slowly. And the solid, this is more normal behavior, the solid will form slowly as it cools down. And when it's allowed to form slowly, the crystalline structure tends to reject impurities. If you're doing sodium chloride. So the sodium and the chloride ions want to come into this crystalline structure where their energy is the lowest. And so if, say, a lead ion or a fluoride ion is starting to get trapped in there, it will get excluded because that would mess up the structure and the energy would not be as low. We make use of this a lot in organic chemistry lab to purify the substances that you synthesize. Rock candy is made by crystallizing table sugar, recrystallizing table sugar. I tried to do this when I was a kid. My son tried to do it a couple months ago, and miserable failures. You have to make a saturated solution at an elevated temperature, and then you have to let it cool down slowly. You're going to have a string or something inside, a stick, for it to form on. If you want to try that at home, I recommend looking up a YouTube video or Googling a recipe to avoid wasting a lot of time.
And sugar.
Pardon me?
And sugar, because I tried it once too, but I didn't realize that it takes like 3 times as much sugar
as the amount of water. Yeah.
So I had a pot like that, and I had to pour like bags and bags and bags of sugar.
Yeah. At high temperatures, sugar is extremely soluble in water. And so, yeah, it requires a lot of sugar. So don't think too big.
Yeah, and you really want a clean jar to put it in, otherwise you get crystallization.
Right. And I think that's one of the problems with Michael's experiment was, it just crystallized everywhere. It was just a big old mess. And I think when I did it as a kid, I didn't have nearly enough sugar in there. And so I waited, days and days and days, and nothing crystallized because it wasn't even saturated at room temperature. So that's where it's helpful to use other people's experience, right? Instead of just starting from scratch, doing the experiment yourself. So that was solids dissolved in water. We can also have gases dissolved in water or other liquids. The effective temperature on gases in water is the opposite of that for solids. The solubility of gases decreases with increasing temperature. And I think we've all had this experience that cold soda, keeps its fizz a lot longer than warm soda. When you pour cold soda, it'll fizz somewhat. When you pour warm soda, it just fizzes all over the place, right? And you have to wait and wait and wait for that to go down. Because the carbon dioxide that makes the fizz is a gas, and it is less soluble at a warm temperature, and so it's going to come out more easily. This also has implications for aquatic creatures that need oxygen. If the lake is warm, if the river is warm, if your aquarium is too warm, the oxygen levels are going to be low, and the fish are going to have a hard time breathing. And this is why thermal pollution from factories can be devastating for fish. You know, here you've got a factory and it's pouring clean water into the river, but that water is warm. That causes thermal pollution in the river. The oxygen levels decrease because of the elevated temperature, and the fish die. That's why, you know, some fish only live in very cold rivers and lakes because they need a higher oxygen level that's not present in the warm water. Pressure has a big effect on the solubility of gases. As the pressure of the gas increases above the liquid, the solubility of the gas increases. And this is why soda cans are pressurized. So here we have an illustration of a soda can. You get the soda here, and you've got dissolved carbon dioxide in here. There's always a little bit of a head space. It's never full completely to the top. There's always a little bit of what looks like air. But it's actually pressurized carbon dioxide. And that's what gives you that psh sound when you open the can of soda. So you open the can, that releases the carbon dioxide, and carbon dioxide begins to come out of solution. And it will continue to come out of solution. Now, if you have a 2-liter bottle and you screw the cap back on, it will continue to come out until it builds up enough CO2 pressure here that it stops it from coming out. But every time you release carbon dioxide from that soda bottle, the level of CO2 remaining in the soda becomes lower and lower. And it has to be the pressure of the gas. It can't just be general gas pressure. And so they used to sell these things on TV that allowed you to pump air into the soda bottle. Like, well, the percentage of carbon dioxide in air is about 0.6%. And so you're not significantly increasing the pressure of CO2. Now, if you took a CO2 canister and pumped CO2 into the bottle of soda, yeah, that would help a lot. You can even recarbonate your soda doing that. But just pumping air into it's not going to help at all. So let's look at what's going on here. So here we have an equilibrium established between carbon dioxide in the soda and in the air. So we have carbon dioxide leaving the solution and carbon dioxide re-entering the solution. At a dynamic equilibrium, the rates are the same. If we increase the pressure by decreasing the volume of this headspace, pushing this down, now the pressure here is greater. That causes more of the CO2 to dissolve. The rate of dissolution is the same. It doesn't affect how much comes out, but it's going to force more of this to go in until it reestablishes a new equilibrium. Does that make sense? Henry's law quantifies that relationship. Henry's law says that the gas solubility, the solubility of the gas, usually it's measured in moles per liter, is equal to a constant times the partial pressure of the gas. And that's usually measured in atmospheres. KH is the Henry's law constant, and that's going to depend on the gas, on the solvent, and on the temperature. So here's a table. I think this is from the second edition of the book, so they may have fixed this typo. It shouldn't be 10 to the fourth, it's 10 to the minus 4. But here are Henry's law constants for several gases dissolved in water at room temperature. And these are in molarity per atmosphere. So when you multiply this by atmospheres, the unit of solubility is moles per liter. So determine the solubility of oxygen and water at 25 degrees Celsius for air exposed at 25 degrees Celsius, exposed to air at 1 atmosphere, assume a partial pressure for oxygen of 0.21 atmospheres. That's pretty typical for air. So there's several numbers. There's 3 numbers in here. We actually only need one of them. So solubility of a gas, we should think Henry's law. And Henry's law is the solubility of the gas is equal to the Henry's law constant times the partial pressure of the gas. They're asking us to find solubility. That means we need the Henry's law constant and we need the partial pressure. Well, they gave us the partial pressure. The air at 1 atmosphere, we don't actually need that. The 25 degrees, we need to make sure that we're getting the correct Henry's law constant. So if we go back to this table, for oxygen, the Henry's law constant is 1.3 times 10 to the minus third molarity per atmosphere. 1.3 times 10 to the minus third. So this is 1.3 times 10 to the minus third molarity over atmospheres. And then that's going to be multiplied by the partial pressure, 0.21 atmospheres. .7 times 10 to the minus 4 molar. So water at room temperature, open to the air, contains 2.7 times 10 to the minus 4 moles of oxygen dissolved per liter of water. That will change at different temperatures. Henry's law becomes significant in medicine, where you maybe have a patient who's having a hard time getting oxygen from air. And so you can get more oxygen into their blood by giving them a higher partial pressure of oxygen. But Henry's law allows you to actually calculate how that's going to work out.